Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Google Agent Tools and Interoperability with MCP. Large language models are impressive pattern machines. They can pass exams, write code, and generate images, but only from what they've already seen in training. On their own, they can't look up today's weather, query your database, or send an email. That's where tools come in. Tools are how we give models something like eyes and hands, ways to perceive fresh information and take real actions. When you combine a model's reasoning with tools that can act, you get Agentic AI, systems that can pursue goals on a user's behalf, not just chat about them. In this context, a tool is simply a function or program that an LLM-powered application can call. The model still generates text, but tools let the surrounding application reach out to other systems. Conceptually, tools fall into two big buckets. They help the model know something by retrieving data, or do something by triggering actions like API calls or device control. Each tool is defined with a clear contract, its name, parameters, and a natural language description, so the model can decide when and how to use it during a conversation. Consider a simple weather assistant. If a user asks, "What's the weather here today?" the model's training data won't contain your current location or today's forecast. Instead, the agent calls a weather tool a function that takes a location, hits a weather API, and returns structured data. It might also call a small math or conversion tool to switch between Celsius and Fahrenheit. The agent then weaves those tool results into a natural language answer. The intelligence is shared. The model plans and explains, while tools fetch facts and perform precise operations. The paper focuses on three major categories of tools. First, function tools. These are ordinary functions you define in your code and expose to the model, often with docstrings that double as tool documentation. Second, built-in tools, capabilities like web search, code execution, or URL fetching that are bundled into the model platform itself, such as Gemini's built-in tools. Third, agent tools, where one agent is wrapped and exposed as a tool to another agent. That lets a primary agent delegate a subtask to a specialist agent without handing over the whole conversation. Agent tools are a powerful pattern. Imagine a general-purpose advice agent that can call a smaller, specialized agent whose only job is to return capital cities. The user talks to the main agent, which decides when to invoke the capital agent as a tool. The main agent stays in charge of the dialogue, but can lean on specialists for specific tasks. Google's Agent Development Kit and the Agent-to-Agent protocol go further, allowing remote agents to be exposed as tools, so you can compose distributed agent systems without tightly coupling them. We can also classify tools by what they enable. Information retrieval tools let agents search databases, documents, or the web. Action or execution tools actually do things: send emails, post messages, run code, or control devices. System and API integration tools plug agents into existing enterprise systems and third-party services. Finally, human-in-the-loop tools explicitly involve people, asking for clarification, requesting approval for risky actions, or handing off tasks that require human judgment. Together, these categories cover most of what modern agentic systems need to do. Tool documentation isn't just for human developers. It's literally what the model sees when deciding which tool to call. That means names should be clear and specific, like create critical bug in Jira with priority instead of update Jira. Every input and output needs a plain language description, not just a type. Long, cryptic parameter lists confuse models, so keep them short and well-named. Examples are especially helpful for edge cases and tricky distinctions. And when you use default values, document them clearly so the model can rely on them safely. When you instruct an agent, focus on the action, not the specific tool. Instead of telling the model, use the create bug tool, say, create a bug describing the issue. The tool's own documentation already explains how it should be used. Repeating or overriding that in the system prompt can create conflicts and confusion. Give the model room to plan and choose tools autonomously. The one place to be explicit is when tools interact. For example, if fetch web page stores content in a file that another tool reads, document that relationship clearly. A common mistake is to wrap a complex enterprise API one-to-one as a tool. Those APIs were designed for expert human developers, not for a model that has to choose parameters on the fly. Instead, define tools around concrete tasks the agent should perform for the user, like create support ticket or summarize customer history. Each tool should have a clear responsibility and minimal side effects. Occasionally, You may bundle a long, frequently repeated workflow into a single tool for efficiency, but that should be the exception, and it must be documented very carefully. Tool outputs should be as small and focused as possible. Large tables, full documents, or images can quickly overwhelm the model's context window and slow everything down. When you need to handle big data, store it in an external system and return a handle or ID instead. Most tool frameworks support JSON schemas for inputs and outputs. Use them. They both document the tool for the model and let your application validate calls at runtime. Finally, treat error messages as another teaching channel. Instead of just saying 404, tell the model what went wrong and what it should try next. As more models and tools appear, integration becomes a serious bottleneck. Traditionally, each model tool pair needs its own custom connector. If you have N models and M tools, you're staring at an N times M integration problem. That doesn't scale. It slows down development, fragments the ecosystem, and makes it hard to reuse tools across applications. The field needs a standard way for agents to discover and use tools without bespoke glue code for every combination. That's the motivation behind the Model Context Protocol, or MCP. The Model Context Protocol, introduced by Anthropic in 2024, is an open standard for wiring AI agents to external tools and data sources. Instead of every app building its own custom connectors, MCP defines a common way for tools to be exposed as servers and discovered by clients. The goal is a plug-and-play ecosystem where agents can connect to any compliant MCP server. This decouples the agent's reasoning and user experience from the nitty-gritty of each back-end integration, making systems more modular and easier to evolve. MCP follows a client-server model, similar to the language server protocol used in code editors. The host is your main application or agent runtime. Inside it, an MCP client manages connections to one or more MCP servers. Each server exposes capabilities like tools, resources, or prompts, often acting as an adapter to some external API or data source. The host orchestrates user experience and security. The client handles protocol details, and the server focuses on implementing capabilities. This separation is designed to support a rich, competitive ecosystem of reusable tool servers. Under the hood, MCP uses JSON RPC 2.0 for all messages between clients and servers. That gives it a lightweight, language-agnostic structure. There are 4 basic message types: requests, results, errors, and one-way notifications. On top of that, MCP defines transport protocols. For local tools, servers often run as subprocesses and communicate over standard input and output. For remote tools, MCP recommends a streamable HTTP transport that supports streaming responses, but can also work in a stateless way. This flexibility lets MCP cover everything from local file tools to cloud-hosted enterprise services. On top of the basic protocol, MCP defines several higher-level capabilities. Servers can expose tools, resources, and prompts. Clients can offer sampling, elicitation, and routes. In theory, this gives a rich vocabulary for how agents and tools interact. In practice, adoption is uneven. Tools are the clear winner. Almost every MCP client supports them. Resources and prompts are supported by only about a third of clients, and the client-side capabilities are even rarer. So today, tools are the main driver of MCP's value, and the paper focuses primarily on them. In MCP, a tool is described using a JSON schema-based structure. Each tool has a unique name, an optional human-friendly title, a natural language description, and JSON schemas for its inputs and, optionally, outputs. These schemas define parameter types and meanings, and they're crucial both for model understanding and for runtime validation. There's also an annotations field with hints, like whether the tool is read-only or idempotent. But these are just hints. Clients shouldn't blindly trust them, especially from untrusted servers. Good MCP tools follow the same documentation best practices we discussed earlier. MCP tools can return both unstructured and structured content. Unstructured results might be plain text, images, or audio blobs. Structured results are JSON objects that should match the tool's output schema. Tools can also return resources, either embedded or as links to external URIs, which might represent files, logs, or other data. Because resources can be risky, clients should only consume them from trusted sources. For failures, MCP supports 2 layers of error reporting: protocol-level JSON RPC errors for things like unknown tools, and in-band tool errors marked with an is error flag. Those in-band errors are another chance to guide the calling model on how to recover. MCP's appeal is clear. It gives developers a common protocol for integrating tools with LLM-based applications, which can dramatically cut down on custom glue code. Because tools are discovered at runtime, agents can adapt to new capabilities without redeployment. Architecturally, MCP fits well with the idea of an agentic mesh, where reasoning, memory, and tools are modular components you can swap in and out. And while MCP's built-in security is limited, its structure does provide hooks where organizations can layer on governance, access control, and human approval flows. Despite its promise, MCP isn't enterprise-ready out of the box. One big issue is context window bloat. To let a model choose among tools, you often have to stuff many tool definitions into the prompt, consuming tokens and confusing the model. That can hurt both performance and reasoning quality. MCP support for long-lived, stateful connections can also clash with stateless, horizontally scaled architectures. On the security side, the initial spec offers only basic authorization flows, with unclear identity propagation and no built-in observability for logging or tracing. Enterprises are already compensating by wrapping MCP traffic in managed platforms and gateways. The paper points to an emerging architectural shift. Instead of preloading every tool definition into the model's context, agents may soon use retrieval-augmented generation for tools themselves. Faced with a task, the agent would first query a large index of available tools, pick a handful of relevant ones, and only then load those definitions into the prompt. This makes tool selection more scalable and intelligent, but it also opens new attack vectors. If an attacker can poison the tool index, they might inject malicious tool schemas and trick the agent into calling them. So dynamic tool retrieval will need strong security controls. Security is where MCP becomes truly challenging. On one hand, MCP is just another API surface that needs the usual protections: authentication, authorization, rate limiting, and monitoring. On the other hand, it's a standard protocol that's being used to connect agents to highly privileged backend systems and sensitive data. That combination raises the stakes. Misconfigurations or malicious servers can lead to unauthorized actions or large-scale data leaks. The paper argues that securing MCP isn't a one-time checklist. It demands a layered, evolving strategy that accounts for both traditional vulnerabilities and AI-specific threats like prompt injection. Dynamic capability injection happens when an MCP server changes the tools it exposes without the client's explicit awareness. Because agents discover tools at runtime, a server that originally only offered low-risk content retrieval might later add high-risk actions, like purchasing or data deletion. The agent's behavior and risk profile can shift overnight, even though the agent code hasn't changed. This is especially dangerous when tools are installed from third-party registries or run outside the enterprise's direct control. To contain dynamic capability injection, the paper recommends several defenses. First, clients and SDKs should enforce allow lists of approved servers and tools, rather than trusting whatever a server advertises. Servers should be required to signal when their tool lists change, so clients can revalidate. For installed servers, pinning tool definitions to specific versions or hashes helps detect unexpected changes. An API or agent gateway, such as Apogee, can sit in front of MCP servers to filter tool lists, enforce enterprise policies, and apply user-specific authorization. Finally, for high-value systems, organizations should host MCP servers themselves in tightly controlled environments. Tool shadowing occurs when a malicious tool is described in a way that makes it more attractive to the model than a legitimate tool. For example, a company might have an official secure storage service tool for sensitive code. An attacker could introduce a Save Secure Note tool with a description that aggressively claims it should be used whenever the user wants to save anything important. The model, reading both descriptions, might choose the malicious tool and send secrets to the attacker's server. No traditional permission check is violated. The planner simply picked the wrong tool. Defenses against tool shadowing start with controlling which tools can even appear. Clients or gateways should check new tools for name or semantic collisions with trusted ones, potentially using LLM-based similarity checks. For highly sensitive connections, mutual TLS can ensure both client and server identities are verified. Policy engines should enforce rules at critical points: before tool discovery, before invocation, and before results are returned. High-risk operations like deleting files or sending external emails should always require explicit human confirmation, regardless of which tool is used. And agents should be prevented from connecting to arbitrary MCP servers, especially those running locally on user machines. Another class of risk comes from malicious or overly permissive tool definitions and the content they process. Tool descriptions and parameter docs are fed directly into the model's context, so they can carry hidden instructions that bias or hijack the planner. Tools that read external content, like files, web pages, or emails, can pull in prompt-injected text that then influences the agent. And tool outputs may contain sensitive data, such as API keys or personal information, which the agent might echo back to users or other tools without proper filtering. Even well-intentioned tools can become attack vectors if their inputs and outputs aren't controlled. To mitigate these threats, the paper recommends classic secure coding practices adapted to agents. Inputs to tools should be validated and constrained, for example, blocking directory traversal or arbitrary shell commands. Outputs from tools should be sanitized before being fed back into the model, stripping secrets, active content, or suspicious patterns. System prompts should be clearly separated from user and tool content so they can't be overwritten. External resources from third-party servers should only be fetched from allow-listed URLs and with explicit user consent. And tool descriptions themselves can be filtered or rewritten by an AI gateway or policy engine before they reach the model. Because agents often pass large chunks of conversation history into tools, it's easy for sensitive information to leak into places it doesn't belong. A tool that only needs a product ID might receive full chat transcripts containing personal data. The elicitation capability, which lets servers ask clients for more user input, can also be misused to request secrets, despite the spec's recommendation not to. Without a way to tag and track sensitive data through the system, it's hard to enforce strong privacy guarantees. The paper suggests bringing ideas from information flow control into MCP systems. Inputs and outputs should be tagged to indicate whether they contain sensitive or untrusted data, often called taint tracking. For example, user free text and data fetched from less trusted systems should be considered tainted by default. Tool schemas can use annotations to mark fields that may carry sensitive information. Then, policy engines can restrict how tainted data flows. For instance, preventing it from being sent to external email tools or public databases without explicit approval. This kind of data-aware control is essential for safe enterprise deployments. Finally, the MCP authorization model is quite coarse. Typically, a client goes through a one-time authorization flow with a server, and that's it. There's no built-in way to express that a given user can call some tools but not others, or that certain resources require elevated permissions. It's also ambiguous whether actions are being taken on behalf of the end user, the agent, or a generic system identity. In multi-agent systems, this makes it hard to enforce least privilege and to audit who actually did what. To tighten access control, the paper recommends using scoped credentials that are bound to specific audiences and actions. Each tool should get only the minimum permissions it needs. Read only, where possible, no shared super tokens across systems. Secrets like API keys and tokens must never appear in the model's conversational context, where they could be echoed or leaked. Instead, credentials should be handled by the MCP client or gateway and passed to servers through secure side channels. Combined with external policy engines, this can approximate fine-grained per-tool authorization on top of MCP's core space. The appendix walks through a classic confused deputy attack adapted to MCP. In this pattern, the MCP server is the deputy. It has broad privileges to a sensitive backend, like a corporate code repository. A malicious user with limited access crafts a prompt that convinces the AI assistant to ask the MCP server to perform a privileged action, say, creating a new branch containing a secret file. The server checks its own permissions, not the user's, and happily complies. The result is privilege escalation and data exfiltration without any direct breach of the repository itself. This illustrates why identity propagation and per-user authorization are so critical in MCP-based systems. Stepping back, the story is twofold. First, tools are what transform large language models from static pattern predictors into agents that can perceive and act. Their effectiveness depends heavily on careful design, clear documentation, task-focused interfaces, concise outputs, and informative errors. Second, MCP offers a powerful standard for connecting agents to tools at scale, solving the integration problem and enabling dynamic modular architectures. But MCP by itself doesn't deliver enterprise-grade security, identity, or observability. The likely future is not pure MCP, but NCP wrapped in robust governance layers, API gateways, hardened SDKs, policy engines, and secure tool design practices. MCP provides the interoperability. It's up to adopters to build the safe, auditable frameworks around it.